In this video, we're going to discuss the concept of absolute and conditional convergence. So it is possible for a series to have both positive and negative terms and not be an alternating series. So for example, sine of n over n squared, which would be sine of 1 over 1 plus sine of 2 over 4 plus sine of 3 over 9 and so on and so forth, is going to have positive and negative terms based on what the number is that's plugged in, but it's not actually an alternating series. So it may be possible to get some information about the series by investigating the convergence of the absolute value of that series. So for this one, I'm going to look at the sum from 1 to infinity of the absolute value of sine of n over n squared. And I'm just going to take a couple of look at a couple of things. I'm going to say, okay, well, the absolute value of the sine of n we know is less than or equal to 1, because if you remember, the graph of sine looks like this, and it's never going to be less than -1 or greater than 1. So from there, I can divide both sides by that positive n squared, and I get that the absolute value of the sine of n over n squared is less than or equal to 1 over n squared. And of course, n squared is positive, so this is really the same thing as the absolute value of sine of n over n squared. And we know that the sum of 1 over n squared is a p-series with p equals 2, so it converges. And we know that if it is greater than this absolute value here, by the direct comparison test, the sum from 1 to infinity of the absolute value of sine of n over n squared also converges. Okay, well, we also know that because this thing right here, this absolute value, is positive, we know that that's always going to be greater than or equal to the sine of n over n squared. So you can look at the direct comparison test again, and since you know that this one converges and is larger than this one, that would also tell you that the sum from 1 to infinity of sine of n over n squared also converges. So we've effectively just used the direct comparison test twice. Well, this is a special type of convergence. Sometimes with an alternating series test, you have convergence because of that plus or minus, that give or take. Sometimes you have just convergence just because, and that's what we talk about with absolute convergence. So if the series, the sum of the absolute value of a sub n converges, then the series, the sum of a sub n is also going to converge. The converse of this is not true. You may have some examples like this one where this converges, but this one does not. So you can't use it in reverse. You can only use it in the order in which it's stated. And a good example of that is what's called the alternating harmonic series. If you verify using the alternating series test that we talked about in the last video, this guy converges because each term is smaller than the previous term, and if you take the limit of 1 over n, you get 0. However, we know that the normal harmonic series diverges. So this type of convergence right here is called conditional convergence, because the sum converges, but the sum of the absolute value diverges. If they both converge, it's called absolutely convergent. So let's look at an example. It says determine whether the series from n equals 2 to infinity of -1 to the nth power times n over n cubed minus 5 converges absolutely or conditionally or converges. So what we really need to see here is we need to check if the sum of the absolute value, and we used 2 here, and I think they just did that to make the denominator defined, so you don't have any issues with there, and it makes everything positive because n 2 cubed minus 5 is going to be positive, whereas 1 cubed minus 5 would not be. So if I have, let's see, I would have the absolute value of -1 to the nth power times n over n cubed minus 5, and we need to see if that converges. So the absolute value of that is basically just going to be n over n cubed minus 5, and that's going to be positive as long as n is greater than or equal to 2, so we'll call that a sub n. And if I were to use the sum of 1 over n squared, and I call this a b sub n, this is a convergent p series with p equals 2. So I'm going to do the limit comparison test. The limit as n approaches infinity of a sub n over b sub n, so that'll be n over n cubed minus 5 divided by 1 over n squared. So that will be the limit as n approaches infinity of n over n cubed minus 5 times n squared over 1. And this will be an n cubed and this will be an n cubed, so that's going to be 1. So by the limit comparison test, the sum from 2 to infinity of the absolute value of negative 1 to the n times n over n cubed minus 5 converges. And then by that absolute convergence theorem, we get that the sum from 2 to infinity of the actual function, the actual series, also converges. And since we know that the absolute value converges, we know that that convergence is absolute. And again, with the one that we were talking about earlier with the alternating harmonic series, if you were to take the sum from 1 to infinity of the absolute value of that, you would get the sum from 1 to infinity of 1 over n, which is the divergent harmonic series. But if you were just looking at the original one for the sum from 1 to infinity of negative 1 to the n times 1 over n, no absolute value, we know that the limit as n approaches infinity of 1 over n equals 0, because fixed number over infinity. We know that 1 over n plus 1 is less than or equal to 1 over n because the denominator here would be smaller. So that checks out. So this one converges by the alternating series test. But when you put these two together, we get that this is conditional convergence. It is not absolute. Now, why we're interested in this is because a finite sum can be rearranged without changing the value of its sum. So this is kind of like related to the commutativity idea. In fact, it's exactly the commutativity idea of addition. It doesn't matter which order you add terms in, you still get the same sum for a finite sum. Now, this is not necessarily true if you're looking at an infinite series. However, if the series is absolutely convergent, then its terms can be rearranged in any order. If it's conditionally convergent, then its terms might be able to be rearranged to give a different sum. So I'm going to show you the second case and how that could happen. So we're going back to that alternating harmonic. The only difference here is I've got n plus 1 in the power instead of n. So it's just going to change the even or odd properties of it. So if I were to just list out some terms, my screen jumped down quite a bit. Here we go. If I were to just list out some terms of negative 1 to the n plus 1 power over n, this is conditionally convergent, I would have 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6. And let me just tell you that we have figured this one out and it converges to the natural log of 2. This isn't something that I expect you to know how to arrive at. This is just a fact. This series, and we'll talk about how to get that in a later section. It converges to the natural log of 2. What if you took these terms and rearranged them though? So let's just say I'm going to group things a little bit differently. I'm going to group the 1 minus 1/2, and then I'm going to stick that negative 1/4 out here. And then I will do 1/3 minus 1/6. And then I'll jump over to the minus 1/8 that we're eventually going to get. And then I'll pick up the plus 1/5 minus 1/10 and kind of go in this pattern. Eventually, that you can see the next term would be minus 1/12, and then you would start picking up the 1/7 minus, whatever comes next. But the idea is that all of the terms are there. They're just in a different grouping, a different order. Well, if I do some simplification, this would give me 1/2 minus 1/4 plus 1/6 from here minus 1/8 plus 1/10, and then you would so on and so forth. And if I factored a 1/2 out of this, I would get 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. This is looking familiar. It's exactly what we started with. Now this goes forever. It's an infinite. So what that means then is that this is the original harmonic series from n equals 1 to infinity of -1 to the n plus 1 over n. And since that has a value, the natural log of 2, this whole thing is really 1/2 times the natural log of 2. So what we've done is we've rearranged the terms and gotten a different convergence value. So that's what can happen when you're talking about conditional convergence, where it's only convergent based on that alternating behavior. So if you have a series that is conditionally convergent, be wary if you find the number to which it converges.